In this video, you'll learn how to build an agentic RAG or retrieval augmented generation pipeline for industrial data using Python, LangChain, Claude LLM, and the Chroma vector database. Step by step, I'll show you how to design an agentic RAG architecture that integrates context from maintenance documents alongside real-time data from your OPC UA server and TimescaleDB. Download and run a vector embedding model locally using Ollama. Store document embeddings in Chroma DB. Build semantic search functions to retrieve relevant context and expose them as tools for your industrial AI agent. Before we dive in, let me show you a quick demo of the finished project, and then we'll go through exactly how to build it. I've built a batch plant production assistant that can decide whether to proceed with production based on raw material availability, machine availability, product recipes, and maintenance schedules and potential breakdowns. For example, if I ask, I would like to produce 5 batches of product A tomorrow. Is it possible? The agent will reason through all its available tools, checking inventory, equipment status, recipes, and maintenance documents, and return a clear go or no-go decision with an explanation. My name is Kudzai Mandi Teresa, and I regularly publish tutorials on industrial data and AI right here on this channel. So if you're new here, please make sure to subscribe so that you never miss any of the upcoming videos. This is part 3 of a 5-part series on how to build agentic AI for industrial systems. If you're jumping in fresh with this video, don't worry, I'll give you all the context you need to follow along. All the code for this tutorial is available on GitHub. You'll find the link in the description below. Okay, let me describe our scenario here. So I have an industrial AI agent that monitors a simulated batch production facility. This agent connects to real-time equipment data through an OPC UA server endpoint, where it checks material levels in our storage tanks and verifies the operational status of our production machines. It also connects to our TimescaleDB plant database to retrieve product recipes, checking exactly how much raw material is needed to produce any given product. Using all this information together, it provides detailed responses to questions like, can we produce 50 batches of product A? However, there is a critical gap in this system. What about all the information that isn't in the real-time sensors or the structured databases? The maintenance schedules sitting in the Excel files and the calibration certificates in PDFs and so forth. This is where some of the most critical production constraints live, and our current agent is completely blind to them. And that's why we want to bring all of this data into the context of our AI agent. Now let's take a quick look at our existing AI agent code to understand our starting point. Our current setup consists of several key components. I have 2 Python scripts that handle our data access. One reads from an OPC UA server, pulling real-time information about tank levels and machine states. The second one queries our TimescaleDB for product recipes and material requirements. And then I have a tools module that takes the scripts and uses the LangChain framework to transform them into tools that our LLM can call. And then we have got the main module, and here I'm using Pydantic's base model to ensure we get consistent structured responses from our agent. For the LLM, I'm using Claude through Anthropic's API, though you could easily swap this for a local model using Ollama, as we demonstrated in a previous video. The prompt template is where we define the agent's behavior. We tell it its role, explain what tools are available, specify the output format we want, and include any special rules or constraints. Okay, so let me quickly run our program to show what our current AI agent can do. Okay, so it will prompt me to enter the number of batches that I want to produce for a given product. Okay, so as you can see, my agent has returned a decision. Say yes, production is possible. And then it explains, it comes up with the reasoning where it actually does the calculation of the amount of stuff that currently in the tanks, and also the requirements from the product recipe. And then it concludes that there is sufficient materials, and then it tells me the current status of the machines, and then it also gives me the current material availability, and then it also specifies the tools that it used. Now, when I ask it something like, can we produce 10 batches of product A tomorrow? So it still gives us the same decision, yes, production is possible tomorrow. But what if we've got a scheduled maintenance on any one of these pieces of equipment, and that information is stored in the maintenance documents? Or what if a calibration certificate is about to expire? So that's what we want to do. We want to build an agentic RAG pipeline to bring in all of this additional context from the maintenance documents. Now, before we dive into the implementation of our RAG pipeline, let me explain how agentic RAG actually works in an industrial context. First of all, there are two main approaches to implementing RAG. There is what is called naive RAG, and there is agentic RAG. You'll find out shortly what the difference is and why we're using agentic RAG. Now, currently, when I send a query to our AI agent, that query goes straight to our LLM. The LLM processes the query, looks at what tools it has available, and then it comes up with a plan for how to utilize those tools to fulfill the user's request. Now, instead of just passing the user's request directly like that, we want to utilize the information in our maintenance documents to enrich the query with additional context. And to do that, we first need to put our documents into a format that makes it easy to match what the user is asking with any relevant information in those documents. In other words, we want to enable semantic search. And here's how it works. We take each document and convert it into a vector, essentially a list of numbers that mathematically represent the meaning of the text. To create these vectors, we use a specialized machine learning model called an embedding model. This model reads text and outputs these numerical representations, which we can then store in a vector database. When a user asks a question, we also convert that question into a vector using the same embedding model. Then we can mathematically compare the question's vector with all our document vectors to find the most relevant or the most similar information. Now, here's the key difference between the two approaches. With naive RAG, every time the user asks a question, we automatically search for relevant documents and force feed that context to the LLM along with the query. It's like giving someone a stack of potentially relevant documents every time you ask them a question, whether they need them or not. With agentic RAG, and this is what we're building in this demo, we don't force the context onto the agent. Instead, we provide the RAG system as a tool that the agent can choose to use. The agent decides if and when it needs to search the maintenance documents. Okay, now let's take a quick look at our complete agentic RAG pipeline before we start building. For our demo, we have a maintenance schedule document that contains upcoming preventive maintenance dates and equipment health scores, a maintenance report with recent equipment issues, vibration data, and spare parts inventory. Now, I'm using markdown files for easy editing during the demo, but in production, this could be CSVs or PDFs or any format from your maintenance systems. For our embedding model, we have two options. We could use a Cloud API like OpenAI's embeddings, but for this demo, I'm going to show you how to run the embedding model locally. And for storing our vectors, we're using Chroma, which is an open source vector database. Okay, let's go ahead and build our demo. First, we need to download our embedding model. And for that, we're using Ollama, which is a platform that lets you download and run models locally with zero configuration. To download it, you just go to ollama.com, download it for your operating system. So I have already downloaded it on my machine. And if I open my terminal and type in Ollama, you can see that it's installed and running. And if I type in Ollama list, you can see the models I currently have. I've got Mistral and Llama, which are large language models. But for this demo, we need an embedding model specifically. So let me show you how to download one. So we go to the Ollama website and then go to models. and then you filter by embedding. So you can see there are several options here, but I'm going to use this one. So I'll copy the instructions to pull the model onto my PC. Go back to my terminal and run the instruction. Now, if I run Ollama list again, you can see that I now have my embedding model. Okay, so I'll create a new folder here. And then I'll place some documents inside the folder. Okay, so I've added 2 documents inside our maintenance docs folder. So let's go ahead and open up and see what's inside these documents. So first we've got the maintenance schedule document. So this document contains upcoming preventive maintenance dates for our reactor, mixer, filler, plus equipment health scores. And then you'll notice here that we've got special considerations for product types. For example, product A cannot be produced within 24 hours after reactor maintenance. Product B can be produced immediately after maintenance, and so on. And we also have a maintenance report document. So basically this document contains recent inspection results, vibration measurements, reliability metrics, and so forth. Okay, now let's build our Agentic RAG pipeline. So I've created a new Python module named maintenance rag.py. So this is the module that's going to be the implementation of our RAG pipeline. It will load our maintenance documents, convert them into searchable vectors, and provide tools that our AI agent can use. So let me walk you through the code. First, we import dependencies. We have LangChain utilities for loading and splitting documents. We have Chroma, our vector database that will store and search our document embeddings. And we have Ollama embeddings, which connects to the embedding model we just downloaded. Now we create our maintenance rag class. So this is where we configure the entire system. We start by setting up our 4 key parameters. First, the path to our maintenance documents folder. Second, the persistent directory for Chroma. This is where our vector database will be stored on disk so that we don't have to re-index every time. And then third, we specify whether to use local or cloud embeddings. We're going to be using local. And finally, we name our collection. So you could think of this as a table in our vector database. And then here, since our embedding model is local, we specify the name of the embedding model that we installed using Ollama. And then next comes the function for setting up our vector storage. So basically this checks if a database already exists. If it does, it loads. If not, it creates a new one. And then we've got the load and index documents function. So this is the function that is going to be doing all the loading of our documents. So here we load all markdown files from our maintenance docs folder. Each file becomes a document object that contains both the text content and metadata like the file name. Okay, now here is an important concept. So basically, long documents are problematic in the sense that for semantic search, they contain too many different topics. So we need to split them into chunks. So as you can see here, I'm splitting them into 100 character chunks with 200 character overlap. So the overlap ensures we don't lose context at chunk boundaries. So each chunk becomes a separate searchable unit, making our searches much more precise. And then finally, we use our embedding model to convert each chunk into a vector and store it in Chroma. And then in this function here, we further classify our document by tagging it with metadata. For example, is it a maintenance schedule? Is it a maintenance log? Is it a calibration certificate? And so forth. And then we've got a semantic search function. So now this is our core search engine. It takes a query, converts it into a vector, and finds the most similar document chunks. So as you can see here, I've got a parameter k equals to 4, which means that we want the 4 most relevant chunks. And we can, of course, filter by document type. Okay, now that we have loaded our documents into the vector database as embeddings, we now want to define actions that our AI agent could possibly take, or possible ways the agent could retrieve context from our documents. So we define these functions that bridge between raw document search and actionable intelligence. So instead of just retrieving text chunks, they extract specific decision critical information that the AI agent needs to determine if production can proceed or not. So here we've got the check maintenance schedule function. So as you can see here, it builds a query for checking for specific context about the maintenance schedule. And then it calls the semantic search function and provides all of this information. And then we've got the check calibration status function, and we've got the check equipment reliability function. So again, here you could see that the query involves checking the mean time between failure reliability, vibration, failure hours, recent maintenance emergency repair, and so on. Okay, now again, since our AI agent is based on LangChain, it cannot directly call our Python functions, so we need to convert them into tools that our AI agent can use within the LangChain framework. So we need to create a mapping between the LangChain tools and these Python functions. So this is what this create maintenance tools method is doing. So basically, it creates the wrappers for our functions. And then as you can see here, it's creating a LangChain tool, specifying the tool name, mapping it to a function wrapper, whereby this function wrapper calls the actual function here. Okay, so before we continue to integrate our RAG pipeline into our AI agent, let us first test it to see it can actually retrieve all of this information for us. So as you could see here, I'm calling these functions directly and providing the product name and the date. Okay, let's go through the response to see what happened here. So as you could see here, it created a new Chroma database. You can see now we've got a new directory here for Chroma. And then it loaded 2 documents, which are the documents in our maintenance docs folder. And then it split it into 9 chunks, and then successfully indexed 9 document chunks in Chroma. And then here, this is a function where it's checking maintenance schedule for product A on August 16, 2025. Can proceed true, which means there's no upcoming maintenance schedule. Calibration status can produce there's no calibration details. And then here, check equipment reliability. We've got the risk low, we can proceed. And then here under getting maintenance context, we can see that we've got the next scheduled preventive maintenance for the reactor on August 25th. Okay, so now let us proceed. Okay, so now that we've got our RAG pipeline working, I want to update my tools module to include these new RAG tools. Okay, so I've already done that. Let's go through the code here to see what we have included. So as you can see here, these were the existing tools. So we had get material availability, get machine state, get product details. And then now we're adding these new RAG tools. So first of all, we're creating an instance of our maintenance RAG class, and we're providing all of these initialization parameters. And then we're calling this create maintenance tools method, which does the mapping of our RAG functions into our LangChain tools. And then here we list all of our tools, including the RAG tools. Okay, so let's go ahead and test our tools here before we proceed to our main function. Okay, so you can see here that we're testing these tools. So we can see our material availability tool retains the material level in our tanks. And if we check here on ignition, you can see that these are the current readings. And then here we've got this tool that returns to us the states of each equipment. And then here we've got a tool that retrieves the data about a product recipe from the database. And then here we've got the RAG tools. So you can see this did a maintenance schedule check. It checked 4 documents, and then it concluded that we can proceed. So again, this one, calibration status check. And since we don't have any calibration document here, there was no document to check. And then we've got equipment reliability check. So it did 5 document checks, can proceed, and the risk level is low. Okay, so now that we've built our RAG pipeline and we've integrated it as tools into our LangChain framework, now let's go ahead and go into our main program for our AI agent and see how we can then integrate this agentic RAG pipeline. So again, here we start by doing a bunch of imports. And then here you'll notice that for the structure of our response, in addition to the decision reasoning, sufficient materials, machine states, and material availability, we have added maintenance conflicts, calibration issues, reliability concerns, and recommendations. So we want these to also be part of that response. And then for the LLM, I'm using Claude from Anthropic. So again, you need to make sure that you set your APIs in your environment variables. And then here I've updated the chat prompt template. So basically we're saying you are an advanced batch plant production assistant with access to both real-time data and maintenance documentation. Your task is to provide a comprehensive production feasibility assessment by analyzing material availability, machine operational states, maintenance schedules and conflicts, calibration status of critical equipment, equipment reliability, and spare parts availability. And then we also, provide the decision process. First, get the product recipe to understand the material requirements, check current material levels, verify all machines are operational, check maintenance schedules, verify calibration status, access equipment reliability, and so on. And we also provide production rules for each specific product. Product A cannot be produced within 24 hours after reactor maintenance, and so on and so forth. And then we also have got decision categories. Yes, all checks pass, production can proceed safely. And then we also add that we need to always provide specific reasons for your decision, quantitative data, clear recommendations for addressing any issues, and risk assessment if proceeding with warnings. Okay, and then here we get all the tools. And then we create an instance of our agent, our tool calling agent. We pass to it the LLM, the prompt, and the tools. And then from there, we instantiate the agent executor, which does the actual execution of these functions if the LLM needs those to be executed. And then here we're extracting JSON from the response. And then this is a function for printing our production assessment. Okay, let's go ahead and run our AI agent with the agentic RAG pipeline included. Okay, as you can see, it's checking. Okay, let us see what was the final response. So here you can see the decision is yes. And we've got the reasoning here. All checks pass for producing 5 batches of product A tomorrow. Material requirements, and then it goes off and does the calculation, which shows how much we've got. All machines are operational, no maintenance conflicts, all calibrations are current, which is obviously maybe not true because we don't have a calibration document. But then again, that actually portrays the reason to really build a robust agentic pipeline, because if you ask an agent to check the calibration and it doesn't find any documents, it might start to make up things like this one. And then here, equipment reliability is good with adequate spare parts. And then here we can see it checks, it gives us the exact amount of material in our tanks. And then it tells us the machine states of each piece of equipment that we're using for production. And then we've got recommendations here: proceed with production as planned, monitor failure state as it's currently idle, consider scheduling tank refills after production run. And then here it tells us which tools it used. So it used the get product details tool, get material availability, get machine states, check maintenance schedule, and check calibration status. Now, while our AI agent can reason over structured and unstructured data, there's still a big challenge. So far, we've created tools for our agent by wrapping Python functions and mapping them as custom LangChain tools. That works fine for one agent, but what happens when another AI agent built with Google Agent Development Kit or one built with the Crew AI framework also needs access to the same OPC UA server, TimescaleDB, and maintenance documents? We would have to rebuild and remap the tools for each framework. Clearly, this approach doesn't scale as more agents need access to the same resources. That's why in part 4, I'll show you how to build a model context protocol server. With MCP, you can standardize how industrial AI agents access data and tools. So you build the integration once and use it across any agent from any vendor without rewriting a single line of code.